Okay, so just to provide kind of a high-level motivation for some of the things I'll be talking about, if you take maybe the most prototypical machine learning problem, which is, say binary classification, and you're tasked with developing a classifier, there's all sorts of decisions you have to make along the way. How much data do I need? Is the task solvable to specification? What model class should I use? Post-deployment, what's going to happen to my classifier if there's any drift in data? And really the approach to answering these questions seems to be trial and error for the most part. Well, picking the right hypothesis class, you try several of them, and then you pick the one that has the highest accuracy on the data that you happen to collect. So what we've tried to do is to package a series of works in collaboration with my colleague Gautam Dasarathi into a test and evaluation framework for machine learning, specifically for high-stakes domains. And okay. I'll just use this. Oh, I see. There we go. Great. So if you think about assurance in terms of software engineering, really there's a set of specifications that are predefined, and you want to ensure that the model complies with these predefined specifications. So in sort of standard software engineering, you follow a model-driven design process where you use some sort of domain knowledge to break the problem up into little parts, and then you validate each part independently, and then the complete system is validated together. But this sort of reductionist approach really doesn't work in ML, especially if you're using deeply layered hierarchical architectures. The individual subsystems aren't necessarily interpretable. And if you want to deploy this thing, it becomes really difficult to characterize the edge cases, what's going to happen, how well the model will work, and so on. So one of the sort of prototypical examples for what happens with AI systems post-deployment is this one here. You have an analyst that's using some model, say, to identify targets of interest. And because of the false alarm rate, they end up getting false alarm fatigue. And they discard the model's predictions altogether, right? So what we'd like to do is to actually develop models that work post-deployment. Have this high-level block diagram. I got this from actually the Food and Drug Administration in their digital health guidance. Provides kind of a nice overview of the various aspects of both the model training and then post-deployment process. Model training, this is sort of standard, right? You have some sort of data acquisition protocol to collect training data, and you train a model using some combination of perhaps domain expert features or other data sources, transfer learning, large language models. And then once you decide that this model works to your liking, you deploy it, and post-deployment, as new live data is coming in, you evaluate the performance of the model, and if it crosses some sort of unacceptable threshold, you go back and recalibrate. So I mentioned this test and evaluation API. I'm going to center this presentation around a few different questions that are relevant for both development of models and then post-deployment. The first is in pre-development, before you even start thinking about developing a model. Is the problem solvable to specification? If so, how much training data is needed? The second is, how do I select the right model class given the training data that I've collected? And then post-deployment, if the model goes out of spec, how do we detect that, and when do we know that it needs to be recalibrated? So the presentation is really focused around classification. Some of these concepts can be extended to regression type problems as well, but I'll kind of highlight those when different parts. Just in terms of some of this work, there's been a lot of interest in the DoD community at large for developing test and evaluation APIs. So for example, a lot of the work I'll talk about today has been used for the ML model qualification process for Army DevCom. This was done, this sort of transition via an SBIR. And then JTIC, so the Pentagon is sort of developing a standardized test and evaluation set for different, for the different parts of the DoD that are using machine learning. And then more recently, we've been working with Raytheon to define transition opportunities there as well for development and deployment of ML models for autonomous low-cost munitions and other applications. Okay, so let's kind of get to this, these questions one by one here. So the first question, is the problem solvable to spec? When I worked in industry, being on sort of the machine learning side, they wanted to develop some new product, and there's of course a sensor and then a machine learning model, say, to classify between two different classes. Anytime the sensor got too expensive, they would offload the processing. They say, well, we'll just build better machine learning models. And you know, if you have some specification that you need to detect some sort of target with a certain amount of accuracy, it becomes very difficult to say whether that's possible or not. Like, can you, if you reduce the resolution of the sensor, are you able to classify between wheeled and non-wheeled vehicles, for example, with 90% accuracy? So this is a problem that I was interested in working on several years ago, and the statement is as follows. You have some underlying data generating process, the real world, and again, a binary classification problem. This data generating process generates samples X from either F0 or F1. So these are two different distributions representing the two different classes of interest. And as you can see, there's some inherent overlap between the two classes in the stylized example, right? So even if you had an infinite amount of training data, there's a certain irreducible error associated with the classifier, right? And so what we're really interested in characterizing is, if you were to train the best classifier possible, what would the error rate of that classifier be? So we defined this notion of distance between probability density functions, so-called DP divergence. So it takes as input the two distributions and computes this density functional. P and Q represent prior probabilities from the two distributions. And this divergence measure, this distance between distributions F0 and F1, has some really nice properties. Of course, so just to kind of backtrack a little bit, from the real world, we only get samples. We have no idea what the analytical expression for F0 and F1 is. And this divergence measure, of course, is an analytical expression that depends on F0 and F1. So as I'll show here, you can actually estimate this using from samples directly without needing to characterize F0 and F1. So what's special about this divergence measure? It has several nice properties, including a certain type of symmetry. It's zero only when the two distributions are the same, and it's upper and lower bounded by 0 and 1 respectively, it's lower and upper bounded by 0 and 1 respectively. And the nice thing here is 0.5. You can estimate it directly from samples, from the samples X, without requiring knowledge of the underlying distribution. And the real reason it's useful in this context is it provides a link between the data and the Bayes error rate. So it upper and lower bounds the Bayes error rate, meaning the minimum achievable error in classification problems. And these bounds are tighter than many of the existing known bounds on the Bayes error. In terms of the sort of the how this works, I'll show this with a simple two-dimensional example. Imagine you have samples from these two classes, the red and the blue here. So these are F0 and F1. This is a simple two-dimensional example, but to estimate this DP divergence directly from the samples, we first compute a minimum spanning tree on top of the data. In other words, you find pairwise Euclidean distances between every point and every other point. And you prune, throw away the high length edges and keep a minimum set of edges remaining. And then I'm highlighting here in green the edges that connect samples from different classes. We'll call that test statistic math-cal-C here. So this is the edges connecting samples from two different classes in our data set normalized by the total sample size. One thing to notice here is when you have a lot of overlap in the data, you see a lot of green because you have a lot of points that are near each other of different classes. However, when the distributions are not equal, the number of green edges reduces, right? You know, if they're completely separable, you might have only a single green edge that connects the red and the blue. So as we showed that as asymptotically, this test statistic basically, once it's normalized properly, approaches this DP divergence. So you can estimate this DP divergence directly from the samples by effectively counting edges from the different classes and normalizing it appropriately. This is an asymptotic results. We subsequently have some finite sample results that shows the rate at which you can do this. And it becomes more and more challenging with increasing intrinsic data dimension. So not necessarily the ambient dimension. You can do this sort of thing on images as well. But the intrinsic degrees of variation in the data. Just to give a couple of high-level examples here. Imagine you have two-dimensional Gaussian distributions, and they start out completely overlapping, and they start moving apart. So you can see here that the Bayes error is shown in blue. You can see the theoretical DP bound is shown in black and the estimated bound in red, and then the Bhattacharya bounds, the ones based on the Hellinger distance in green. Several remarks here. The first is that these DP bounds are tighter than the Bhattacharya bounds. The second is that the Bhattacharya bounds actually require knowledge of the underlying parametric analytical expression, so that the parametric model of the distributions here. So in this case, we told them that these were Gaussians. And of course, the Bayes error decreases as the mean separation between the two Gaussians increases. So this is to kind of show this sort of result in a stylized two-dimensional example. We've also looked at sort of a meta-analysis where you look this kind of famous Pima Indians diabetes data set. What we have here in the green boxes is the set of all published accuracies on this data set, on this benchmark data set, and then the lower bound and the upper bound as estimated by this DP divergence to kind of show that they bookend the published results. So that's an example of estimating this DP bound. Now, everything I've shown here is sort of on relatively low dimensional data sets. How do you actually scale this to real world data? So the key thing to look at is the reason that scaling this to real world data is challenging is because you're effectively finding distances between points in order to generate this graph. If what you have is a series of images, the Euclidean distance between two images is who knows what, right? So as an alternative, there's recently been some nice work on differentiable graph losses, so where you actually can estimate sort of a soft version of this test statistic, this math-cal-C, that counts the number of edges between points of different classes. And you can train a discriminative encoder to minimize that value. So you're effectively squeezing or learning an intermediate representation of the data that is maximally separable with respect to this dp divergence. That removes the redundancies away, and if you estimate then the dp divergence on the learned embedding, you get a much more reasonable estimate of the true divergence measure. So this is sort of the approach we've taken on scaling this to real-world data. Let's see, a couple of other extensions. So you can see some of those results here in this last paper, where we actually used this approach to regularize deep learning models. And we've extended it to multiple classes and then regression bounds based on a similar approach a few years ago. Of course, here there's no such thing as Bayes errors. We're looking at bounds on the mean squared error. Okay. So, okay, now just to kind of back up a little bit. So this is the bound on the minimum achievable error. Why is this useful? What's the purpose for testing and evaluation? Well, there's, of course, lots of different ways to measure distances between distributions. The nice thing about this dp divergence is that it's anchored to this Bayes error, which is something that actually provides actionable information to algorithm developers. So it can help answer the sorts of questions like, what are the bounds on the minimum achievable error? Can I meet the spec? So if it's required that I achieve an accuracy of 85%. Is that within the bounds? Should I proceed with the problem? And then if you look at individually which samples contribute to this error, in other words, where in feature space do these samples that or connect points from different classes reside, there's ways to identify the ones that are contributing to this error. So in terms of actionable information, you can decide whether to continue searching for new models or whether the current model falls within the BER range. Detecting overfitting if, for example, the accuracy falls outside the bound, or underfitting. And yeah, I mentioned this, determining which samples. So let me move on to the next. So this second point is, if you've now decided that the model is solvable to spec, the next sort of question is how much training data is needed. And the starting point for this type of analysis is the learning curve. This is sort of an amazing phenomenological result. It's like if you look at learning in the context of machine learning models, if you plot average accuracy as a function of sample size, they all seem to follow this nice functional form, this power law model. So people have used this power law model to fit to human learning as well as you increase the number of samples. So this is interesting. I mean, you can now, if you have a parametric model that fits this learning curve nicely, you can use it to extrapolate and to see what the accuracy would be if you had additional training data. So the basic idea is as follows. You start with a data set, and at a fixed n, you do bootstrap sampling to get to sample a subset of the data. You train a model and then evaluate it out of sample on the remaining data, and you do this while iteratively increasing n. You get a series of points here, so x is sample size, and the blue points represent your estimates of model accuracy as a function of increasing sample size. Now you can fit these points to the parametric learning curve model, and this can help answer questions related to sample size. So the sorts of questions are for example, if you have, let's say, this model an to the minus b plus c. If you look at these individual constants, they're quite helpful. So C tells you what the accuracy of the model would be if you had an infinite number of samples, right? Because the first term goes away. And so if you had this is sort of the maximum performance of the model. So that's the red line here in this stylized example. If in addition to this, you have something like the bound on the Bayes error, so perhaps the bound on the Bayes error is a bit higher than that, that would tell you that this particular model class is unable to reach the Bayes error. And so if you're really interested in squeezing all of the accuracy out of this model, you may want to consider an alternate hypothesis class, one that results in a higher C value if you do this sort of this analysis. So just to kind of to reiterate that, the idea behind these learning curves, these are a function of both the data and the model class. The DP divergence is only a function of the data. So the DP divergence tells you some underlying, it's basically an estimate of an underlying property of the data, the amount of overlap between the distributions. This gives you an estimate of performance if you condition on a particular hypothesis class and train it with the data. So the sorts of questions that it can help answer is how many samples are needed to achieve performance within epsilon of the Bayes error rate or some specification, and to help determine if there's a change in the hypothesis class needed, and to determine how much additional training data is needed to achieve performance within some tolerance of the Bayes error rate. This particular model, I don't have it included here, but one of the nice extensions that we've been working on recently is, it turns out the academic literature is filled with models that are likely overfit. And so if you, across many different domains, if you do a very simple experiment, you look at classification models and plot the reported accuracy as a function of sample size, you notice that that has an inverse relationship, which is quite unexpected, meaning models trained with fewer samples report higher accuracies than models trained with larger samples. So that's probably a combination of both overfitting and then also publication bias, like only the people with the highest performing models report them. So we have a certain measurement model that's centered around the learning curve to try and effectively undo this. So to get a sense of how much over-optimism there is in a given field in the published literature using these learning curves. Okay, so move on to the next one. How do we select the right model class? So certainly the standard way to do this is you evaluate a series of model classes and then pick the one that results in the lowest accuracy, in the highest accuracy, lowest error. We wanted to go a step further to see, can you say anything about how the model is classifying? So not just what the underlying accuracy is, but rather what is the decision boundary that the model learns, and does it match that of the data? So imagine you have a training data set. Again, I'll use kind of a stylized example to highlight this. It's a binary classification problem, red and blue again. And what we're interested in doing is to characterizing the shape of the decision boundary for separating between these two classes. Of course, in 2 dimensions, you can sort of see this visually. This becomes interesting in higher dimensions. And to really characterize the shape of the decision boundary, we rely on characterizing its topological structure. So starting with the assumption that the decision boundary is a manifold, We create a simplicial complex, this sort of check complex. It's basically a collection of edges on the data. You start with a sphere around each point and iteratively increase the size of the sphere until you have overlapping spheres between nearby data points. And this approach allows you to characterize, so for each value of scale, for each size of the sphere, you get certain points that intersect, right? So at different scales, the shape of the resulting data is different. The way you characterize this shape in topological data analysis is through these Betti numbers. These Betti numbers describe certain property of the shape of the resulting structure. So H0, for example, represents the number of clusters in the data. H1 represents the number of loops and circles in the data. You can think of these very broadly as descriptors of the underlying decision boundary in this case, and at different scales. So these properties change as a function of scale. As the size of these epsilon balls grow, you get different collections of edges that you can analyze to extract these features from. So in a couple of papers, actually our collaborators started this work from IBM. So the theorem 3 in the first publication here specifies the conditions needed for this check complex, this collection of edges, to accurately reflect the decision boundary's topological features. So in other words, this is a process to estimate the topological structure of the decision boundary. So the theorem 3 in 1 specifies the sample complexity. How many points do you need in the data in order to ensure that this check complex, this simplicial complex, accurately reflects the true topological feature, so the so-called homotopy equivalence. And then in 2, we actually extended this framework to the active learning case. So how do you learn the structure of the decision boundary if you have a series of unlabeled data points and an oracle that you can request to iteratively sample certain points? So this is both of these main results. Sort of the key takeaway is that the more complex the decision boundary, the more samples you need to accurately characterize its shape. So how is this useful? Well, at a very high level, you now have a descriptor for the shape of the decision boundary. And so if you use a data set and use it to train a series of models, you can compare this persistence diagram, this representation of shape, learned by each model versus that of the data, and select the model that has the decision boundary most closely associated with that of the underlying data set. So rather than relying on just accuracy as a metric, you rely on the underlying, the shape of the learned decision boundary and how it compares relative to the shape of the decision boundary in the data itself. We have a sort of a model selection task in the paper where we're looking at training a series of pairwise binary classification problems. So MNIST, Fashion MNIST, and CFAR10, these are all 10-class problems. So we generate binary classifiers for each set of pairwise classes in each data set. And we look at the idea of transfer learning, so learning on one set of classes and then testing on another set of classes. The underlying hypothesis is that you'll get higher accuracy if you use decision boundaries that are better from your transfer task, that are better aligned with that of the task of interest. And again, for the sake of time and lunch, I'll go ahead and skip the details, but this this has applications in some of the work recently where you're starting with a specific foundation model, for example, and you're fine-tuning off of that. So identifying sort of the right foundation model to start with. Model marketplace type examples. So again, utility for testing and evaluation. Is the true decision boundary from the data the same as the decision boundary learned by the model? And in terms of actionable information, determining whether to continue searching for new models or whether the current model captures the true decision boundary. Okay, the last question that I'll go over, again, we'll come back to that DP divergence. It has this additional nice property. It's really focused on answering the question, does the model need to be calibrated? So post-deployment, you get incoming live data that is not labeled, right? You have no idea what the label of the data is. And you'd like to be able to detect that the model has failed and that it should be recalibrated with either no additional labels or perhaps only a small subset of labels. So just to highlight the data drift example, right? You have some source data set that you're using for training, and then post-deployment, you have this data drift or this covariate shift condition where as time passes, as conditions change, the underlying distribution shifts from the original one. So now the source distribution is shown here in the lighter colors, and then the target post-deployment distribution is shown in the darker colors. And the fundamental question to answer is, how is the accuracy of a classifier trained on the source data impacted when there's covariate shift post-deployment? So it turns out, again, in the same paper, we have this other result where if you look at the source and the target distribution, FS and FT, so these are not class conditional distributions. This is the actual source and the target distribution. If you look at this DP divergence, where you have an equal number of samples, so with equal prior probabilities, P equals Q equals a half, between the two, you can bound the target error, so the post-deployment error, based on error on the source data plus this divergence measure between source and target distribution. So if there's a lot of covariate shift, then the bound on the target error increases. If there's no covariate shift, then you get that the source and the target error are, the target error is bounded by the source error. And the kind of, again, another stylized example here. If you have on the x-axis days since deployment, you might imagine each one of these points here is an estimate of this DP divergence between source and target distributions. Again, you don't need labels in order to estimate this value. And tracked over time, if you have some predefined acceptable error, the moment that the model crosses that error, that might signify a retraining event, something that you would want, where you'd want to take action. So this is sort of one way to use this. The one thing I'm not talking about here, again, this is in collaboration with Gautam Dasarathi. We're looking at this idea of including active learning type frameworks post-deployment, where you identify specific samples that are especially informative for detecting model drift or for estimating model performance. So that if you have the ability to query an oracle to label a small subset of points post-deployment, then you can do that, rather than here where it's done in a label-free way. The problem with doing it label-free is this is really the model assumes a worst-case type, the bound is a worst-case type bound, where small changes in the source distribution result in large changes in the bounds. Right, so the sorts of questions, again, has any data drift occurred post-deployment? If so, what is the impact on the accuracy of the originally trained model? And in terms of actionable information, if you detect, it's going to allow you to detect, say, catastrophic failure, really events that change the performance of the classifier suddenly. And so at that point, you may want to take the model offline altogether. I'm going to go ahead and end there. I'll have a series of some of the results that I discussed are in this subset of papers, although there's other relevant ones. So I'm happy to take any questions.